Okay. Hi, I'm Dwight Elvey. I was asked to talk about this project that I'm working on. Um, it seems a couple of years back, a company called GoTech, I believe they're in Japan, they decided that a lot of these old Casio keyboards and things like that had floppy disk drives in them, and the floppies were becoming obsolete, and they needed to do something so that they could people could still use these machines without having to pay out another $600-700 for a good keyboard. Well, the floppy emulator that they had, which I tried to show here a few seconds ago, but I'll try and show it again here, is this little module here. It uses an STM32F105, which is a 32-bit processor, and it's also capable of being a USB host, which is the way it works, and for the purpose they're using it for. So it's actually a pretty powerful little processor. It has 64K of RAM and 128K of flash for your program, so it's a pretty powerful little thing. The idea would be is that you would have a USB thumb drive, and you would stick it into the front, and then you could put your files on it, as many files as you wanted up to. In this particular case, it could have up to 1,000 files for the original arrangement, which is pretty good. My purpose on it, though, is that I'm trying to get it to emulate a SA800 with using it with hard-sectored formats, with 32 hard-sectored formats where the data continues to write even over the sectors. So in other words, the application I have actually has 2 sectors per track of 16 sectors wide. So the way that they've set up the software, it really depends on the index signal being separate from the data. So I'm looking to see if I can make it work with my my application. What's shown on the screen here, if you look at that, this is a company called HXC, and they have provided firmware that you can download into these little GoTech boxes with for just about every standard kind of floppy application that's out there. Say you have an old TRS-80 or an Apple II, and you'd like to hook up a floppy, you can get the floppy emulator from these guys here. They cost about $20, and this GoTech costs anywhere from, depending on where you get them, about $15 to $20 also. So for about $40, you can replace your old floppy on your machine, whatever it is, put everything on a thumb drive, and you don't have to worry about the motor giving out or the heads getting cruddy and have to clean them every now and again, all of those other kinds of problems. So what I've started working on, and I haven't, the first attempt didn't work, but I know why at least part of it didn't work, is I've been trying to take Dr. Ting's fourth, the E4 that he has, and get that up on this particular processor. He has it on a F407 processor, as I recall, and it's enough different than the F105 that I needed to make quite a few changes. One of the things that it doesn't have that the 407 has is the ability to remap the RAM to different locations. Without that, that means I have to run it at its original location. So there were some minor changes involved in that. Luckily, he'd put the switches in there. The switches were still in there, so I was able to switch most everything. The other part that's bad is that the ports, many of the ports are completely different and at different locations in the memory map. All the ports are memory mapped in these processors. But I've made some progress. I've written my own downloader for it because I don't want to be beholden to some company for their downloader, and because it's really not a complicated process. I've had to figure out a couple of things on there on the STM web page. They have all of the information for writing a downloader, but Yeah. No, no. This is HSC. This is They have a downloader that they give you with their software, but the downloader I have is one that I wrote by myself. Okay, based upon the what is ST something. God, I can't remember what the name was. Yeah, no, yeah, but STM is a ST micros is what STM stands for. I don't know what the ST stands for, but anyhow, they're the ones who manufacture these processors, and but you have to dig a bunch to find everything. But once you get the first document, there's links to other documents, and what's also good about this particular implementation, once I get it running, is most of the people, when they buy the little STM processor for the Arduino setups, they'll be getting the 103, F103, which is a variant of this one. And this firmware is designed to work on the whole family. So the downloader I have and the code should actually run on these other processors with very minimal modification, without any extra fiddling. So we can get eForth onto those as well using this version. There are several forths available through GitHub, but they all require somebody else's licensed element someplace along the line, and most of them are just because of the downloader, right? And the downloader, it's taken me about a week to get it working, because even with the manual on it, some of the descriptions are not correct for what is really being necessary to make it work. There's a number of interesting variants in there, and the one that got me the most was that the way you do the checksums for a byte is different than the checksums you do for multiple bytes. And they only showed you how to do it for the instruction part where it's a single byte, but they don't show you other places where you have a single byte again that you have to use, that you have to do a slightly different checksum. So that makes it a little, certainly different than what they described. Also, a lot of the times they don't tell you that you have to be on 4-byte boundaries everywhere. That they tell you that for the end address, but they don't tell you that for the start address. And everything needs to be on 4-byte boundaries. And that also is another interesting difference between this one and the one Dr. Ting. Dr. Ting's, when you write to flash, you write as four whole bytes. In other words, you do 4 bytes at a time. Whereas this one, you have to write it as a half word, which is only 16 bits. So I had to rewrite that section of it. I haven't tried it out yet, but it should work. But you write it as 16 bits at a time rather than a full 32-bit transfer. So little minor differences like that I've had to come across. Most of it should just work. So I hope to get it working within the next few days, actually. To talk to these, you need to get a, let's see if you can see this. I don't know, maybe if I get a little closer to the... Yeah, no, this is a it's a serial, like an RS-232, but it's 5 volt and 3.5. No, it's not a level shifter. It's a USB to it's a USB serial to an RS-232 like signal, but it's a 5 volt ground and 5 or ground and 3.3. And you really should run this on a 3.3. But they say the inputs are 5 volt capable, but you really should be running at 3.3.
Probably an FTDI.
Yes, it is. As a matter of fact, this one is. But there is that other type. I forget what it is that starts with a C something or other. But I think it uses the same loader. Yes. But yeah, this one here was one I got off the web.
I'm not sure whether the C stands for competitor or China.
Yeah. But anyhow, this only costs like $3, $3 or $4, I think is what I recall, including shipping. So at that price, it's who cares, right?
Should I impose upon you? Are you on the email list?
Yeah, I get the.
If you could send links to this thing,
GoTech.
this thing.
Okay.
And you say, some of your tools
Yeah.
You have links to documents that you want to send out?
I could send you my source files.
Yeah,
They're
that'd be great.
they're just in they're just in Win32. There's some cleanup I'd like to do, of course, because
Get it all working and stuff.
yeah, it's working now, but the downloader requires that there be 16-bit. All the hex lines are 16 bits, so I have to pad them.
It's really exciting, but it's Tim's turn now, so
Okay,
sit down.
I'm done.
We'll harass you at the break.
Okay, would you like the microphone?
Yes, he's got to have the microphone.
Just gonna make noises for a second here.
Thank you for letting me drag you up
Okay.
there, and thank you for letting me drag you down.
Yeah. Okay. Thank you.
Okay, I think I'm on. Okay. Is this one doing anything?
If you want to, if you turn it on, let me turn it on for you. With the power button, signals.
Okay. Well,
Hold the button with the power on, and there you go. And it should be working.
Can you hear me now?
oh yeah. Okay, that's good. Okay. Okay.
You got to get right up to it. Yes, it has to be very close for it to be, and
But,
it has to be pretty, if you want to raise and lower it, it's down below.
Yeah. There you go.
Okay.
There you go.
All right. I'm CH10, and this session is not it's fourth related, okay, but not fourth. Non-coding DNA in C Runtime. So let me just get started. Last time I was talking about my mitochondria, which is actually the smallest genome of all the living things. But a mitochondria is not freestanding. It has to live in a cell. Okay, so it requires a lot of support from the cell, and so its genome can be very small, only about 16K. And I thought, well, 16K, I can handle it. So I take a look at it and found that the non-coding DNA is only 1 kilobyte. I said, well, 1 kilobyte I can manage, but I look at it, but couldn't make much sense of it, because for 1 kilobyte, I don't understand how it can accomplish all the things that it does. Okay, and among that 1 kilobyte, only 309 bases are the critical code, and it's just couldn't do anything with it because the data set is so small. So I thought, well, let me go to the next bigger freestanding genome, and that's the C. rudi, and it is an endosymbiotic protobacterium, and it has the smallest genome of any free living organism. The genome is a circular chromosome of 173,802 bases, and of this amount of bases, 227 genes were identified. But that's not what I'm interested in. What I'm interested in is in the non-coding DNA. And there are, from the database in the genome, there are 40 DNA sequences which are named hypothetical proteins. That means they don't know what it's doing, okay? It looks like a piece of code, but it's not coding any protein. And the total length of these 40 DNA sequences about 14,000 bases. So I thought, well, that's a big enough database to really do some research and searching, and probably I can find something there. So I extracted these 40 sequences and hope to find program segments in them to reveal how life forms are programmed in DNA. Because if we look at the cell, it is a computer, okay, for all purposes. And we know lots about the DNA, especially we call the coding DNA. And these coding DNA are genes. Basically, they are encode proteins. They are genes which produce proteins to carry out certain cell functions. And I call them primitive instructions in a cell computer. So these are actual functions that the cell has to produce proteins. And the proteins actually go out and do the work. And these are the primitive instructions in fourth language. Non-coding DNA. Well, nobody really knows what they are doing, okay? And they contain, my assumption is that they contain the programs and the data which control all the cell functions. And the cell functions are accomplished by producing proteins. And the proteins has to be produced in a program sequence in order to perform their function. And so I believe that the non-coding DNA contains the data and program which control all the cell functions. And they contain the high-level instructions in a cell computer. And so that's my assumption, okay? Because you know how a cell is actually doing their very complicated things. Not just, well, they are accomplished by producing protein in program sequences. But how these program sequences are controlled, I believe it is in the non-coding DNA, because there's nowhere else. That's all the information there is. You have coding DNAs and you have non-coding DNAs. But we believe that all the DNAs control the entire function of a cell. So these are the high-level instructions in a cell computer. But how are these high-level instructions encoded? And non-coding DNAs contain object code in a cell computer. So if you look at the DNA code, just as if you look at a piece of real computer code, they contain instructions, objects on how the computer functions. But unfortunately, the cell computer, we have only the object code. We lost the source code. So we really don't know how things are how functions are performed, except that we know that the coding DNA produces certain proteins. So if we look at if we believe that all the program and data are contained in the non-coding DNA, I believe it is possible to decode the object code and perhaps reverse engineer the cell computer in all life form. Okay, so if information are contained in this part, we should be able to to read it and understand it. So this Rodi genome, this is the starting part of the entire genome documentation. Okay, and it has certain assignment, the code, and it has 173,802 base pairs, and these other things are for the database management. So I found that there are 227 coding DNA, coding sequences, and they have assigned what type of protein they produce. But these 40 sequences are designated as hypothetical proteins, and there's no and that means they don't know what they're doing. I assume that these are the non-coding DNAs and contain data and programs for various cell functions. So, you know, as we are programmers dealing with code all of our lives, and we have encountered occasions that you get the object code with no source. And if we knew certain things about this code, for example, if we know the host computer and we know the instruction set, then we probably can read the object code and then reverse engineer a program. So, what I did was extract all the sequences in text form for me to inspect and to analyze them. So I tried to, I got 14,000 bytes or 14,000 bases to look at. So that's a sizable chunk of information. I have to devise various ways to look at this data. I have to look at it globally. I have to look at it locally. So I try to use different views to look at this data. And of course, the first one is a text form. So the Genome Project published the entire sequence and all the assignments. So these are very interesting documents that contain all the information there is on any particular live form. So I take out a text and look at the text, and I try to do fixed pattern analysis. I want to analyze the data and to see if there are fixed patterns in it that I can identify. Of course, the goal is to find the tokens in the non-coding DNA. And if I can identify tokens, just as if I can identify machine code, then I can decode the entire program. So this is another way. This is the fixed pattern analysis. This is the easiest way. I just said, well, I will analyze ACGT. Okay, what's the frequency occurrence of AAAA or AATT? Any of this pattern, and I can do fixed pattern search and do the statistical analysis. And I can also, I believe that tokens must be repeated patterns. Any intelligence is about repeated patterns. So to search and to analyze repeated pattern, I use a graphic view to look at them graphically, and I also try to use tables, Excel tables, to put all the data in a huge amount of data in two-dimensional form and try to look at them and try to understand them. So these are the several. So I have to build lots of tools to do this analysis. So this is the text form inspection. So I can just extract one segment of non-coding DNA. And these are actually copied off the genome data file. And usually they would give you the base number and then 10 bases in a sequence. So these are the data presented in the original genome file. So here I was looking, before I look at anything, I said, well, is there anything interesting? Okay. So, from my pattern analysis, I was able to identify the longest, all the repeated pattern in a segment. And generally, I said, well, the most interesting data probably is the longest repeated pattern. So here I have tried to identify the longest repeated pattern in a segment. And if you look at this code, you probably would see that there's lots of repeated pattern. The A is repeated very frequently, and T is also repeated very frequently. So I try to, put them in color and try to see if it makes any sense. Okay. Well, yeah, doesn't make much sense, but I can identify lots of patterns in a segment of non-coding DNA. So this is the primary base of information that you can look at and see and make sense of. So this is the text form inspection. And so when I try to do the fixed pattern matching, the text representation of DNA is ACGT. These are the 4 different bases, and they are generally use ACGT to represent the 4 different bases. But this is just like ASCII characters and the binary numbers. The text is very inefficient. It is suitable for human reading, but not very convenient for the computer manipulation. So if you can convert this text representation into binary representation, here I'm using 0 to represent A, C to represent 1 to represent C, 2 for G, and 3 for T. And the binary is 4 times compressed, because you have one character which is 8 bytes, which is 8 bits, and you can use only 2 bits to represent the base. So, if you convert into binary, the volume is highly compressed, and you can manipulate these numbers much easier. Then you can just, anything. Well, we have lots of tools to manipulate the text, but we have much more tools to analyze the binary numbers. So, it's just like Forth is very, very good. We have been doing this by converting ASCII to binary and binary to ASCII. The most powerful feature of fourth is that it jumps from the external representation of numbers in ASCII to internal representation of binary very easily. You can, when you need to see these numbers, you can convert them into ASCII, and when you want to process it into number, you can convert ASCII numbers into binary. So, I'm just using fourth this mechanism to do the external and internal conversion. So here is the one example of the fixed pattern analysis. I'm analyzing 4 bases. Okay, so this is AA for a row and AA for a column. So 4 bases. There are 16 patterns. So you get 16 and 16 to contain the result of the pattern analysis for 4 bases. You need 256 slots to store the frequency. So what you do is you take one segment, one sequence, and then using a 4 bases window, just scan the entire sequence, and then drop and increment particular slot if you find a particular pattern. So here, if you analyze 4 bases, you have 256 slots. And when I analyze all 14,000 bases, all 40 sequences, this is the frequency table. And you can see that AAAA and the TTTT, these are the most frequent pattern.
That's amazing.
Yeah, it's very very interesting. Just like what we saw in the text representation, you can see that AAAA and TTT occurred quite frequently, and this is the actual result for a complete analysis of all 14 sequences. And from this, you can see a very interesting thing is that A and T occurred much frequently than C and G. Okay, so this is actually what they call the GC poor sequences. GC is a pair, and AT is another pair. Generally, GC, when the sequence of DNA, when a genome has lots of GC, the strand is heavier because G and C are heavier than A and T. So when they separate the DNA pieces, usually they go into the centrifuge, and they can separate the GC strand from the AT, GC-rich strand from the AT-rich strand, because generally you have 2 complement strands, and one strand is GT-rich, and another strand is GT-poor. So you can always separate the strands. But in this analysis, you can see that the GC, especially when you have GC together or GG together, the frequency is very low. And you have AA together, you have TT together, the frequency becomes very high. And so, so I think this table generally shows you the frequency of occurrence of bases when we analyze 4 bases. So we can do better. 4 bases, we need 256 slots. If we do 5 bases pattern, we need 1K slot. 6 bases, we need 4K. 7 bases, we need 16K, and 8 bases, you need 64K slots. So, 255, we can display the entire table on 1 page. But for 5 bases, you need 4 pages to see result. And then 6, 7, 8, it's just the table gets so huge, you just can't see them all or do any sensible analysis. So here, I thought that, well, okay, since I don't have GC is poor, so when I display the table, I just the columns, the rows which contains G and C, because A and T, these are the prominent components, and I think there are more information in the A and T components than G and C, A and T than G and C. So when I encounter any C rows, I just skip them, and then that keeps the table relatively small. So I have the 5 bases. It actually has 4 pages of code if you want to display the whole thing. And this is 6 base. And actually you have 4K rows. And if you skip all the G and C, you got a much small table. You can look at it. And if you want to do the detailed analysis of the individual patterns, you can see A, 6 contiguous A, you have 211. The frequency is much higher than anything else, except this one, T. Okay, and all the other ones are about 1/2 of the frequency of these 2. But you might this one is kind of interesting, and this is interesting. So just by looking at the frequency, we can see that contiguous A patterns, repeated A patterns, and repeated T patterns, these are special. Yeah.
How special are they?
Very special.
I'm thinking that they could be delimiters, that they're not really interesting at all. Maybe the repetitive is saying, get ready for something that is actually interesting.
Yeah.
I don't know.
Yeah. I don't know yet either. I would think that A will be a call instruction, and T will be a return instruction. If that's a 4th computer, but we don't know. But this pattern is interesting, and if we want to understand the significance of it, and this table gives you lots of things to think about, because there are this is the highest, this is the next highest, okay. And I think that you should pay more attention to these highly frequent patterns.
Look for the patterns that follow long strings of A and T. Those might be where things actually happen.
Yeah. Could be.
There's one other question that asked me. I know that genetic material is not always 100% doing something.
Right.
There are bits and pieces because of mutation, which are not affecting the
They're never expressed.
right. So it's possible that the longer sequences that you're seeing are actually those pieces that got damaged at one time and are no longer doing anything. So
very
maybe the
could be.
medium length ones, which are actually probably more useful. The really short ones, I doubt, could do much of anything by themselves.
Well, that's why we originally talk about these junk DNAs.
Yeah.
And they didn't do anything. Okay,
Yes.
they don't produce protein.
Yeah, well, they're not junk, but they do know that some of them do, tell the proteins
Other
to
things.
start and stop.
Yeah.
Make more of these, don't make more of these.
Yeah. That's what I want to find.
Yeah.
These are the program.
That's the program.
That's program. These are not proteins. Okay.
Yes.
And so we found that lots of A is very frequent, and lots of T is very frequent. What do they mean? I don't know. But so intelligence is always hidden in repeated patterns. Always.
There are almost repeated patterns that are almost identical.
Yeah.
How do you swap those?
Yeah. And I think it's a exactly repeated or similar. Okay. But intelligence are always in a similarity. Okay. If things are random, you can be sure that there's nothing hidden in it. Okay. What's hidden in it are the repeated patterns. And the high level.
Looking at the number pi, you'll see that it does have repeated sequences. They're pretty much uniform.
Right.
There's no consistency.
Okay. High-level programs are mostly consisting of subroutines tokens. Yeah. These are what I'm looking for. Okay. So are there tokens that we can identify them and find out the specific functions of them? So tokens, what I want to find in the non-coding DNAs are in general tokens. Are there tokens which perform a specific function? Okay, so to do the pattern analysis, what I found was very effective is that for each non-coding sequence, they can be up to 1,000 bases long. I would just take one sequence and use a 50 base window to scan through the pattern and save all these 15 base data in a file. And when you have 15 bases records in a file, then I just give that file to Excel and ask Excel to sort all these patterns. And when Excel finishes sorting, it's putting all the repeated patterns next to each other. Okay? So this is, I think, the very effective way to find all the repeated patterns. Okay. So when you search through it, you can basically see all the patterns sorted, and all the patterns which are similar to each other in the sorting order, and they are next to each other. But looking at 1,000 of these records, it's very tedious. And so I wrote a small program to display the repeated pattern by drawing the matched pattern. So you have lots of patterns which are sorted. And if I can compare one pattern with its next neighbor, and see and ask how many bases are matching. So this is the length of the match, and I will just display the length of the matched patterns, and this will give me an idea on how this how the whole thing is okay. Let me just show you the pattern. Okay, 40 bases. Each one is sorted, and then this height shows that it's the identical to 16 bases are identical. Okay, and this is about 10 bases. So you can see you have many. You can see the pattern of matched length in a sorted order. Here, to make it more interesting, I would color the bases. If I color the base, for example, if I color A with black, B, AC with red, and G with green, and T with blue, and so this one would look like this. The whole thing is, if I color the first base, okay, and this one is the start with A, okay, and this start with G, and this start with C, and this start with T, okay. But I'm coloring the second base, okay, because the first base I know they are of A, is B and C, and A, C, and GT. I'm coloring the second base, and so you see in this whole A, and this part is AA, and AC, and AG, and AT. Okay, and this whole part is start with T, and this part is TA, TC, TG, and TT. So it's just more interesting. Okay. If I color the third base, then it's going to be very confusing, because you will have you will further divide this thing into 16 patterns, and it's going to be very busy for your eyes. But this shows that all 40 non-coding DNA, their distribution of likeliness in their sequences. And some of the things is very interesting. For example, you can see that one, which has a triangular shape. And this is actually showing that you have a very long T pattern. And then when you scan it, the T will be the last. If you have one less T, it will show up one slot before. And one T smaller, and you will have a slope. And this one, you start with you have a very long repeated A pattern, and then it just scan through its neighbors, and you got lots of related pattern, but it's sloping. So you can see here, because I'm sorting everything, so all the A occurred here, all the T occurs here, and then A get less, and T get more and more and more. So So this is interesting patterns that you can learn from it. And another important thing is that of all the patterns, the longest repeats are 16 bases. Okay, so I have not seen any repeat pattern which is longer than 16 bases. So that's another thing. And then you can see A is covers very large region, and T covers a large region. And then this one is the C part, and this is the G part. So C and G has only about 12% of the entire basis. So 88% of the bases are A and T. So of course, when you have so many A and T, they tend to repeat, and they tend to dominate the matched pattern display. Any question? Okay, so this is a very nice display that I loved, and I was struck by the small amount of GNC in this in the non-coding DNA. So I look at the coding DNA, and I have all the data in mitochondria. So I just gave the entire mitochondria to the analysis, and you can see that the distribution is very different. Okay, here you see the first A covers this one, and then the C covers here to here, and then G is up there, and T is the last. So you see the A and the G, A, C, and G and T. They are roughly about the same length. Okay, so in the coding DNA, A, C, and GT are generally of equal distribution. So I was very surprised at the Runtime. Well, G and C is very has a very small portion. So it is very much different from the normal view of coding DNA. So I don't know. So these are the only two organisms I look at, and they have very strong disparity. And I think I need to look at more to see if this GC poor feature is common to all the other organisms. But I'm not sure. But from reading some of the data on the general genome text, I think most organisms in their genomes, the G and T and G and C and A and T, they are about equal. Okay, there might be a 10% difference. Have you looked at the synthetic? No. I think I need to look at more bacteria before making any.
But I mean, they have the synthetic one, which they believe is the smallest so far. It's the smallest amount of genome that you can make a self-repeating growing organism.
Yeah. I think they just, I think they do not understand fully the non-coding DNA. They just take a portion of a bacteria and just stitch together all the genes and to see if it's alive or not. Okay, but I'm not. I don't know. At least I haven't seen any report about the detailed analysis of the non-coding DNA, the function of non-coding DNA. So I have another interesting view of the non-coding DNA is to use Excel. So I can basically what I want to do is Excel. I can put all the patterns in one column, and I have 40 of them, so I can put all the 40 different sequences in a single table. And the idea is that if you put everything into a single Excel table, then you have a global view of all 40 DNAs. And if you arrange the patterns carefully and try to match the pattern between the sequences, then you can do a local comparison on which pattern seems to be the most prevalent in all the sequences. Yeah, well, yeah, I think we should be careful not to say anything about things we don't understand.
Even the remnants may have purpose.
Yes, yes.
I'm just saying that for each organism has its own priority for doing things, even though they may be similar, right?
Yeah.
So that means there may be pieces that are. It's just like us. We have appendix that we don't need. We have.
You don't know.
No,
Hey.
What?
Appendix, you need it. Okay.
Yeah.
Okay. Well, let me just move on. Okay. So I was trying to see if 40 columns is really too big to see on the computer screen. So I think, well, I take 30 bases, or just 20 or some, and short sequences less than 500, and long sequences, and separate them in 3 tables so I can actually look at these tables. So here is the median strand, 500 bases. 300, I think it's, I forgot whether it's 300 or 500. You can see if I display them and then move the columns, move the data in a column vertically so that they would match each other. And there, I should be able to see the similarity much more clearly. So on top of course, it's A, and then down here we got 6 A's, and then followed with T, right? And then so I cannot do it automatically, but for this table, only 500 rows, I can kind of manually move things around and get. Let me show you. Yeah. Okay. So this is the real data, and I'm trying to move all the T. This is where the TG started. So this area, I move everything into this areas of rows so I can compare them across. So it's still very tedious. I think we need to build the tools to automate these things.
Well, I was going to ask, have you seen anybody interested in the same type of thing and throwing this at a neural net? Throw it like big data. Let a big data analysis system look for patterns.
Well,
because I suspect the pattern's bigger than you can hold yet.
That's right. That's the problem.
Yeah.
Okay? Yeah. For 16,000 data bases, I can still handle them manually.
Maybe.
Yeah. If I work hard enough.
Right.
Yes.
You gotta consider the isotopes on the
Hmm?
isotopes.
Nah.
Yes, that makes all of the different species of animals.
No. Well, yeah, we got enough trouble with these, with carbon. Okay. Uh-huh.
A lot more extrapolation.
Yeah. We want to assume the assumption is that all the organisms are built on the same basic principles.
Yes,
So,
but we also know our minds can't do much more than 7 things. We have a limitation on our minds.
Yeah. We need a computer to do it.
And that's why I'm saying, go
Yes.
to a neural net.
Yeah. Okay. We have real neurons here. Okay. So let's try to use the real neuron before we have to.
True. Before you have to go to artificial.
Yes.
See if you can see it.
Okay.
Let
me see.
Don't discourage you.
Okay. So I will just share you with some of the observations. I don't think I understand what I'm doing, what I'm seeing, but these are observations. I think that's interesting and probably quite important. For the rhodite non-coding DNA, we have very low GC content. Okay, it has two possible meaning. One is that GC is not important. We don't need it. Okay, A and T are sufficient for coding purposes because we only need 0 and 1, right? For all the computer programming. So 4 bases is really not efficient. So GC might be just happen to be there. Okay, it doesn't serve just like you say. It may not serve any purposes, useful purposes. So this is we can see these things this way. In another way, GC bases are very important. Okay, so it's this G and C which are actually control all the other A and T. Okay.
I mean, it could be like us in our semicolon and colon.
Yeah, right.
Important part. Without it, you don't know where to start and stop.
Right. So you can we have to look at this way. No, we don't know, but maybe GC is not important. All we have to do is analyze A and T. Maybe we have to pay much more attention to GC and look at the patterns they involve. Okay, but we have to be open to both these possibilities. And we have I've told you AAAA and PTTT, so most prominent repeated patterns.
If we were to, or if some net were to examine popular speech, it might conclude that either and are very important or are not important because they're just so popular. It must carry a lot of information. Otherwise, what good is it?
Yes.
I'm not sure.
Yeah, exactly.
Okay. And are they tokens? I don't know. We need for a programming language, we need a lot more tokens. Okay. But it seems that A repeats and P repeats must play a very important role. And then the other things which has the A and T mixed in certain proportions. For example, AATT is half a small frequency like AAAA and TTTT. So is TTAA. Okay? So AATT, TTAA may have special significance as well. Okay. So we have to look. We have to compare. So if I take one of the longest sequence, which has 1175 bases, and just look at the T and A repeats. Can you make any sense of it? No, I don't know. Yeah. Well, you know, if we make, for example, if we restrict ourselves to 8 or 9 A and T, that might space out those patterns quite a bit, which may make more sense. Okay. But these are the all the repeated patterns more than 4. And they are all over the place. Okay. I think they are very, very important, very significant, but what do they mean? I don't know. Okay, so I have some observation. Genome is a huge text file of bases. And when they are in a cell, it's binary. Okay, and these are they represent portion of it represent coding DNA, and they are proteins, and non-coding DNA just plain text strings. So we need to build lots of tools to look at this thing in different ways. So I was using fourth. I have the F# fourth, which has a graphic capability. Of course, fourth has all the text analysis capability if you care to program it that way. So pattern search, string comparison, pattern analysis, all this code that I wrote in F#, except the Excel. Okay, Excel is very nice to give you two-dimensional view of huge data set, which I think I cannot reproduce it very easily in Forth, but since Excel is so prevalent, you just take your files and manipulate it in certain ways, and you just cut and paste, put it into the Excel file, and then do all the convenient things you can do in Excel file. So, you know what lies ahead. You have to be able to handle real big data, okay? Because mitochondria, 16K bases, and rudi, 170K bases. And when you go to real bacteria, it's millions of bases, and you have to be prepared to handle that amount of data.
Always.
Oh, it's much bigger, much bigger. Yeah, when you have a warm multicellular organism, it's much more complicated. So there's no conclusion that I can offer you. Mitochondria has very small non-coding DNA, but it's not sufficient to draw any conclusion. And C. rodi has GC pool non-coding DNA, which may not be typical of other organisms. And we need to go to bigger and more prevalent genomes to see what's really happening out there. Oh, I forgot one. Okay, here. E. coli. This is one of the bacteria that we understand most. It has 4 megabases. Of course, human genome, you and me, got 3 gig. And fortunately, 3 gig now fits on a DVD. Okay, so you can copy the human genome project onto a DVD and then work with that.
No, processing. You can copy the genome, but you certainly can't copy a project, because unless you say the project is the genome. The project is going to involve a lot of examination of the genome.
Most of the genome database, they have analysis in it. Analysis. Yeah, it's not just a pure, basis. It has, the header in it. Tells you from basis N to M. This base meant to produce such protein. Okay, so they have done all this work.
And that's in the 3 G.
No, it just the genome is one-dimensional, but they have been able to identify the primitives or the code of the genes. Okay, a gene is a piece of DNA which encodes one piece of protein. Okay, so all the genes, they have do the analysis, and they have identified the best they can all the genes that exist in a certain genome. Okay, so that information has all been in the database. But if you look at the different, there are different versions of the genome, and they differ. People using different method to analyze them, and they try to identify, and they may disagree on the individual proteins a gene encode. Okay. Yes. These are what we know. The coding DNA, we know they encode protein.
But you don't know their function.
The non-coding DNA, that's what I try to analyze and study. But I'm new to this field. I don't have a general feeling about the general field of genomic research. Well, there are important information. They have identified. I think one.
If we were cows, we would have a much bigger appendix.
but we have lots of understanding of this genome, especially related to diseases. Okay, so people pay more attention on the gene variations when people are sick. Okay.
It may be something you'll need later.
One of the more interesting things that they've discovered recently is that the genes in producing my fingernail spreads, which are in my finger, right? Those genes have been corrupted over time, and that the parts that are necessary to make my liver work may be broken in the ones that are generating my fingernail, but the body doesn't care because they're only making fingernails.
And liver. And onions.
There's a lot of potential research there by actually just taking cells from different parts of the body and finding out what mutations have happened in those different parts of the body that don't appear to be killing the body. You know?
Yeah.
There's a lot of potential information out there.
Yeah. So
the problem is that, like he says, you have to start at some kind of fundamental level, which means you got to work with really small organisms to start with. Working on something like the human genome, you have to sample millions of people's fingernail cells, and millions of people's, or billions probably, in order to get just a hint of what the difference is between that and the one that does.
I think this is what diseases can be very importantly. That we don't know the normal function of genes until we find somebody was sick because of the gene defect. And then you can identify this.
We don't know the total inside of it. We don't know how that interacts with the other pieces.
No, but I think we have identified single base alternation which causes diseases. Okay, so that's very important. But I think as far as the non-coding DNA part, we at least I haven't seen much report. But I wasn't in the field and didn't keep up with the literature, so I really don't know. But what my intention is that as a programmer, I have lots of understanding of the code, and I design computers, so I know what it takes to make computer run, and especially in fourth, that we have this very strong delineation of primitive code and high-level code. And I think this analogy is important in our study of genes, because I believe that the non-coding DNA is important, and they contain data and programs. And I think as a programmer, I can look at the code and make an effort to understand it. Okay? So we still need to, I studied only 2 organisms. And I think to understand the whole picture, I need to be brave and go to many more bigger organisms and try to, in order to make a general conclusion about anything. Okay. Any more questions? Thank you very much. Okay.
We'll take a short break. I want to tell you a cool thing. They did a study about the bacteria on people's skin. And it turns out that the skin on my elbow, the bacteria that are there, are closer to the bacteria on Dennis's elbow feel closer to that.
Oh, good.
I've noticed that about on your feet too.
So as it turns out, there's a theory. There's a repository for the bacteria in your lower GI.
Yeah. It says talk, I guess. Woof! You think
I
I'm...
wasn't looking for that, but
Wish I just keep talking pointlessly and walking around the room and... Oh, good.
You are on the internet. I can hear you.
All right.
State your name.
I... Okay. All right. Where should I stand, by the way? I want to be...
You want to be seen?
I'm okay with being seen.
Well, then you stand in front of the screen.
All right. Fair
When
enough.
you want to be seen, stand in front of the screen in the center.
Right.
The screen is where I'm focused at.
Got it. Okay. All right. We'll move right along.
My name is.
Say who you are.
And get on with the show.
My name is Robert Saxton, and I have a problem that I like Forth, and I work with it every day. So this little project started a couple of months ago when Jurgen said, it'd be really slick if your stuff ran on these little tiny cheap boards that everybody likes over here in Europe. We'll get into that. And so I had written this thing called Sock Puppet, which is basically a tiny little system call layer that you can just drop Forth on top of. So the intent is that you take some vendor-supplied C, you kind of roll it up into a set of 3 system calls that turns on your clocks, initializes your hardware, and then boom, you don't have to write a bunch of bit twiddly crap and Forth, which is just kind of a time suck. So there's a lot of M0 parts out there. Let's see if we're gonna get there. We go. So this is the thought was, what's a nice platform for tinkering, and the application was, say, high school robotics, where you got a bunch of kids and you want to encourage them to learn how to waste their time like professionals. So significantly, with all these things, you want something with low barriers to entry. It's a non-starter to tell people to go buy software in this application, this situation. You want cheap hardware. JTAG probes, this is also a non-starter because JTAG probes are kind of in the realm of professional software people who do this stuff all the time, and most hobbyists either don't have them or you have to buy them. And even we have this great situation now where you can actually buy really nice little JTAG probes. You can buy standalone ones for like $50 or less, so they're attainable. But the other thing is that there's a lot of vendors who supply JTAG probes on their development boards. In fact, I have one. I have one right here. This is the board of choice. This is an ST Micro Discovery board, and on one end there's an integrated JTAG probe. You can get open source software to drive this and program it, and then there's a controller. That said, JTAG probes suck, and mostly because they're really not tools for beginners. They're tools for experienced people, and it's not really a pitch that you're going to make to some 16-year-old, go get OpenOCD, do all these magic incantations that make no sense to you, onwards. So JTAG, I don't use JTAG at work. I do embedded work all the time. I have an entire system that's built around never using JTAG debuggers just to do my job. That's what Forth is essentially debugging in place. So that's kind of the criteria. Robotics competitions, boom. So let me talk about you all probably know I really like Cortex M's. I mostly work with M3s, which was the original design, and it's about a 10-year-old design now. It's a nice, clean 32-bit thing. The M0 was ARM's project to essentially destroy the 8-bit microcontroller world, and frankly, they've succeeded because they've pretty much destroyed most of the benefits of 8-bit microcontrollers. The M0 is a 32-bit architecture, and its most significant feature, in my opinion, is it's got this interrupt controller that is just fantastic. You can do all kinds of great stuff with it because it's prioritized and highly efficient and really fast. It has good debugging features built into it, although we'll get into why the M0 kind of sucks for that, because in the effort to get the M0 into a low gate count device. If you're trying to basically replace an 8-bit microcontroller with a 32-bit microcontroller, one of the things you rip out is most of the really nice debug features. So it's got a pretty basic debug system. You can stop programs, examine memory, that kind of thing. I'll get into more details on that later. And it's also a simple architecture, and it's low power, and it's very cheap. I don't know what ARM's deal is on licensing, but they appear to be giving the design away, because you'll notice it's kind of going into every little device on the planet at this point that was previously in the 8-bit space. So yeah, they're taking over. Let's see. Yeah, so this was kind of my first time trying to do something complex with the M0. And I learned a couple of things that made me think, I'm not sure I want to use this processor unless I have a compelling reason, like I'm going to build 100,000 of them. We'll get into that more. So the things they took out, the M3 has these really wonderful fault diagnosis registers. You can write a fault handler that stops, and you can look at registers, and it will tell you exactly where in your code you did an illegal operation. So it's got fault diagnosis registers that are really nice. The other thing that it's missing is this thing called the vector table offset register, which is a really handy thing if you want to have runtime interrupt vector management. So on the bigger chips, you can say, hey, just move the interrupt table over here so I can modify it at runtime. On this device, you can't do that. It's actually pinned architecturally. So there are things that they took out to save gates and costs that are just missing. Backporting is kind of strange because I wish I had the picture. The M0 is basically 25% of the instructions that were in the M3. So the architects essentially did things like said, we're going to take out this 32-bit instruction. You can use a pair of 16-bit instructions that do the same thing. So it's a really interesting thing. All of a sudden, it's like, well, I would love to have post-increment indexing addressing modes in my chip. And the answer is, no, sorry, you can't have those. But you can manually increment the register yourself with the separate instruction.
Look around 16 bits, replacing the 2 16-bitters replacing 32 bits.
That's actually what I found in practice is that when I would port code from the M3 down, I would find that it would not get longer, but there would be more instructions. So typically you'd be so yeah, it's not as efficient as its bigger brothers. But that was very weird. It was like, wait a second, how come this code didn't get bigger? It's doing the same stuff.
Does it have the same alignment issues that you have to start things on 32-bit on 4-byte boundaries, or does it?
I would.
You start on 16-byte boundaries.
You mean instructions or data?
Yeah, instructions.
Instructions are allowed.
No, I mean for like a call or a jump or something like that, because the 3 requires you to start on a 32-bit.
I would take exception with your characterization that is an issue. That I think that's a pretty normal RISC processor requirement that instructions be aligned in a machine situation. The Cortex, I don't think there's actually a word alignment requirement on the M3 either. I think it's just 16.
I think it is.
I will.
I was reading.
I'll have to look at that. That's interesting because the M3 and 4 have 32-bit and 16-bit instructions. So 16 bits ought to be legal.
Well, no, 16 bits are legal, but you can't jump to a 16-bit boundary. You have to jump to a 32-bit boundary.
I'm going to have to look at that. That's a really interesting. But now, in fairness, that should not be your problem.
Yeah. No, it isn't really an issue, except for it does waste occasional bytes. Because you have to realign at
yes.
boundaries.
Yes. So. Hopefully your product isn't living or dying, and whether or not you can have those bytes. But
there's plenty of bytes.
There's plenty, right? Exactly. So this is the other one that came up. I use NP all the time because I'm lazy and I'd rather just write a check and have a product and use it because I build stuff. Everyone's got some people like writing interpreters. I'm into that. So I work with NP a lot. They have this thing called Lite, which is essentially free for hobbyists. And like all these things, it's stripped down pretty far, So the idea is that you should really buy something if you want to be nicer. But yeah, it's a compiler. It compiles native code on the machine, so it's nice and fast. You don't have to buy it for the little stuff. One of the things that's interesting is it's Windows only, but I run under Wine. It's a very, so for all you cheapskates, just put Wine in your machine, or if you don't have Windows, anyway. And it's got instruction sizes. The documentation is good. It's out there, but anyway, let's see. So let me talk a little about Sock Puppet. Sock Puppet's a system call layer that you've probably seen the slide before. This is kind of an evolving platform for building systems. Sock Puppet last year was put into MPE 4th. You can just go get it from MPE now, and they give you samples of how to use it and how to work with it, that kind of thing. I offered it to them, and they took it. So, and then most recently, I've just finished porting it to the M0, which is actually more work than I thought. I used to say to people, well, it's very similar. Just take that M3 code and no, I'm really sorry about that. It's more work than I thought. Because the M0 has a lot of funny little rules about things it can't do, and then you have to learn these the hard way. Like this instruction mode's missing, So anyway, so here's what I've had to do. There's a system called Dispatcher, and in an M3 you can retrieve something with an index that's multiplied by 4. You can do word addressing. M0 can't do that. You have got to do the math yourself. So it's stuff like that. The other thing, I've set it up so that you can, because the target in this case is amateur robotics, kinds of tinkering, hacky people, the basic model is I'm going to give you a binary that starts up your processor, and in this case has some USB services, and I don't want to put you in a situation where you have to modify it. Because you might not have a C compiler lying around, and it's not really fair for me to send you off to the internet to go get something to this is not what we're about. So the design intent is that it's a chunk of static code. It's essentially a bootloader. So you're just going to load it up in your 4th and run it, which means the system call table needs to be in RAM so that you can modify it later. And I don't have to, if you want to add some new system calls, you can do it yourself. Let's see. Yeah, and then architecturally, the Cortex-M is a dual stack machine. It doesn't have to be, but it is. You usually have exception stacks and user stacks. And so many things work better that way. It's really good for privilege separation. The other thing that's kind of interesting, I rewrote some of these things, and they work just fine on bigger architecture. So it's like, well, why would I write this twice? It already works once. So that's true in some cases, and others. In the case of like a system call Dispatcher, performance matters. So it's worth maintaining 2 sets of binaries. For something like a launcher, which is essentially the way you launch 4th is you take an exception, and then when you unroll all the exceptions, you get to the last one, which is going to launch 4th. And what it does is it monkeys with the system stack so that when you turn from the exception, you're just running 4th. So it's doesn't matter if it's fast. The other thing, I've been playing around a lot with dynamic linking between 4th and C, because ideally you would have this lump of C code and it'd be easy to call it in 4th. You want to have runtime linking. So there's kind of a new system so that when you launch 4th, you can give it a vector and you no longer have to have statically addressed memory or fixed memory addresses. You get rid of that stuff. There's just a structure that C owns. You tell 4th where it is. All is well. What's that? Exactly, and that code is online, but the way I do runtime linking is there's just a table, and it contains 4th words and C vectors, and you can just look at, if you're looking for so there's software that walks the table and creates 4th symbols from the table. So at the prompt, your functions just have names, and you can just call them. The other thing is I finally figured out, I wish does anybody have a pointer? Yeah. Okay. The other thing that was kind of an interesting thing that I've since figured out how to do, and I'm going to keep doing it. I used to partition things statically. I would say, okay, well, the first 16K is for C, and everything else is for 4th. And that's actually kind of wasteful. So it turns out, I'm sure not to look into that.
Yeah, it's the green button there.
Thank you. So I've kind of figured out a recipe for how you can do this stuff dynamically. So this is the memory that is going to the primary executables, and then you can essentially load the bootloader into place. And the thing about their compilers, they essentially compile everything in memory. So you just have this bunch of memory, and you can just modify it. So you can, I can, for instance, modify this binary right here. This binary is going to drop into memory at the beginning. And then this function, data file, returns the size of the thing that was put into memory. So you can do a little math. You can duplicate it, and I can stash the size in the image so I can tell how big things are. And then you can do things like you can pad it out nicely. And then, this is the part that's nice, you stash the location of fourth in the master vector table so that when the bootloader starts up, it doesn't matter where fourth is. It just goes and looks it up, and you no longer have to do this kind of fixed partitioning stuff. So that's worked out pretty well. I think there's also a lot, yeah, you got to pad things out. So anyway, so demo time. So the things you need beforehand, you need wine. If you're not on Windows, do you run, Brad? Do you run Windows on that machine?
No, Linux.
That's what I thought. You're smarter than that. So yeah, it runs fine under wine. I'm running, my Mac, which is more or less Unix. Wine, and then there's this MPE-like compiler. Here we go. So let me take over, and I'll start doing a basic demo of what development what development looks like in this environment. All right. Give me just a moment here. So let's see, are we over here? Over here. There we go. This is going to be interesting. I don't know if I can do this. Just give me a moment, please. Let's see. Yeah, I don't think I can actually do this all in one little. No. I don't think. All right. Let's just try the one window approach here. Let's see what that gets me. Well, that's not what I meant at all. Can you see me here? I can't. Just a moment. Great, now I still can't see what's going on. I'm gonna have to stand up and look at the screen here. Here we go. Voila. Okay. So, boy, that's beautiful. So, all right. Right. So let's crank up wine. So wine wants to run inside of a shell. And it sets up a bunch of environmental stuff, and so it goes. So I've got a project here. This is the MP distribution. And then I'm not going to go ahead and do a git clone because that's in the slides. But here we go. We'll just go with that one. So I have here a basic MP fourth setup. And there's a control file that kind of specifies how everything's set up that I'm not going to get into right now. But this is pretty standard stuff for them. It's basically just pulled right out of their distribution. And then, let's see. So what I'll do is I will launch the one. I'm going to launch their compiler. And then this is kind of the way they do it. You include their control file. It's just essentially a fourth interpreter. So, and then I got to get the path right, of course. I think that's it. And of course, it's going to spew a bunch of garbage, but voila, look, Windows running on a Unix machine. Yeah, magic. So it of course, you know, ran the whole thing. There's logging available, that kind of thing. It pulled stuff in. You can see it tells you how big all the things are it's bringing in. And then at this point, I'm sitting at a prompt. So I've got access to a fairly full-featured fourth setup. Here's all my words. There's, you know, this is all native code, so I can let's see, I can disassemble some words. You know, this is what it compiled for negate, etc. So let me show you what things look like here. So one of the things, let's see, we gotta figure out where we are. Right, we cloned. Right. This is in the slides. I don't know how many people here know how to use Git to pull things off the net, but I supplied all the verbiage. So yeah, you compile it. Okay. So the other thing that you're going to need for this application is there's a protocol called DFU, Device Firmware Update, and it's pretty much a USB standard for how you update devices in the field. It's USB based. So, you know, here we go. So let's try something a little crazy. Photo booth. There we go. No, I apologize. See if I can get this. I don't think you'll be able to see it. There we go. So, I wonder what's going to happen here. Look at that, magic. So this is the back of the ST microboard, and of course it's flipped. Sorry about that.
Just take a minute. There you go.
Yeah, you're not getting it?
Yeah, we are seeing it now.
Okay.
It was black for a second.
Ah, so on the back it says, but it's reversed, right?
It's fine.
Okay. So it goes. So one of the things that the ST microparts have is they have these bootstrapping control pins, and there's one called boot 0. And if you read the fine point in the documentation, it essentially says, pull it high, and you'll force the board into DFU mode. So there's a little jumper right here. So all I'm going to do is put the jumper on there. Voila. Oh, go. Yeah.
It was, but that's okay.
That's all right. So,
People will figure that.
yeah, I think that's not the end of the world. There's pictures. So, yeah, it's a great party trick. Absolutely. So this board has two USB ports. There's the center port, which is the debugger, and we're going to use the user USB port. So now I've got the board in DFU mode, and now that it's in DFU, I'm actually going to remove the jumper because it's in the mode, so I don't need to essentially, you know, push on it. And then, so there are plenty of utilities out there in the world. Let's see. So I'm finished. I just compiled my binary. We're done. I'm going to say goodbye, and bam, I can have my machine back. So there's lots of DFU utilities in the world. I'm using an open source one called DFU Util. You can just, you know, I'm sure there's easy to get packages out there. So let's just run it. So it's going to talk to the device, and now it's uploading the flash into the board. Voila. You notice it's a 40K binary. It could probably be made smaller. So now I've just DFU'd the data into my board, and I took off the jumper. So I'm just going to press the reset button here, which is that one. And for those of you new, you can now see it's blinking. So there's a little heartbeat. I know the board's in its correct mode. And now I'm going to just connect. I'm going to connect to the USB C.USB. So this is a USB CDC device. It's a close relative of the FTDI stuff that everybody knows and loves, which is not actually USB CDC, but that's a different story. And then, bam, I got a prompt. One of the little kind of annoying bugs is that I haven't written any code to buffer up the initial startup from the board, so I can just, reset it, run cold. So now I've got a, a working system here. I can do things like, examine memory. Let's see. So I can dump out device memory. I can, compile a word. That kind of thing. So I now have a live system. The other thing that I've switched to on the Sock Puppet API stuff is I've integrated the multitasker into everything, because blocking is a really nice thing for software. But let's see if I should write up my cue sheet here. Let's see. I think I had a little demo for y'all. Pictures, pictures, pictures. Right. So this is kind of the basics of, how you do. So I can, I can create a task at runtime. So I can generate a task. Oh, I don't have to forget. That's all right. Right. So let's make a variable counter 0 counter plus. So we make a little counter, and then I'm going to make a word that just pulls the counter, increments it, and then calls pause, so the tasker can get a view into things. And then here we go. We just, except I can't cut and paste. Let's see, right. So this is MP syntax. I take the word, I attach it to the task, and I initiate it, and now I have two tasks running on my machine, and you'll notice that the counter is incrementing, which, see, I did not make any of this up. So I got two tasks running. I can block them, stop them, that kind of thing. So
This is a non-preemptive.
Yes, it's cooperative. Yeah.
One of the things I thought about doing with that is that if you make the task loopable, you have the same task multiple times in the loop, you can increase its
Oh, you could, yeah.
priority.
Yeah.
I did that once with temperature control a long time ago.
Yeah.
I found that the temperature controls, I had 50 temperature controls to run, and one human interface, so that the temperature controls got higher priority than the human interface, which didn't require as much online.
Yeah, you could definitely implement a lot of techniques for scheduling. So one of the things architecturally about this chip that is going on here is that sort of the optimal way to make it work well is to put it into low power modes all the time. And essentially what you do is there's an instruction called Wi-Fi, or wait for an interrupt. And the thing that's nice about that is that the chip will be off when there's no work to be done. And then if you integrate that into your scheduler, which I've got the code up for that kind of thing, essentially what happens is the scheduler goes to the loop, and then when there's nobody runnable, it will Wi-Fi the processor, which means that it's very cheap to keep things, a lot of tasks sort of bubbling. So you can do things like for scheduling, you can do things like have a bunch of idle tasks and then periodically wake them. So that's kind of the other way to attack the scheduling thing. So, right. So they've supplied some demo work, here's sorry. Here's kind of how you do things like run a GPIO on this device. MP has some code that they just supplied for free. So anyway, so demo completion. So yeah, here's kind of what's the stuff that's coming up. Systems programming is my hobby. So the thing that I'll present on in the spring. The Cortex-M architecturally has a really clean design for interrupt handling because, traditionally you have in subroutine calling and procedure calling standards, you have call-R saved registers and call-E saved registers. And the interrupt controller does its stacking in compliance with the procedure calling standards of the architecture, which means in practice that interrupt handlers are incredibly fast because the code that they call already expects these rules, so the code doesn't have to do things like stack a bunch of registers. It just does its normal thing, and it's already the way it expects. So if you're writing in C, what means that on this processor, an interrupt handler is just a void function. It doesn't have to know anything special. There's no veneers or pre-starts and that kind of thing. Forth has a bit of a problem in this area because in a Forth, you've got essentially a virtual machine environment, which means that in order to run Forth code, you have to have a data stack, a return stack, a user area. So there's some overhead in just sort of building an environment. So the current state of affairs is that the Forth interrupt handlers, they have to generate the stack on the fly. So when you go look at this stuff, what you'll find is a bunch of code that essentially does a lot of math at runtime and says, okay, well, let me allocate some stack space and some user space, and then, okay, now I'm going to call your word. So it's very inefficient. Now, maybe that doesn't matter to you. I don't know. But it depends on your application whether or not you actually care about interrupt latency. I care.
When are you doing interrupts that you don't care?
Right. Well, sometimes it doesn't matter so much, but I've got some evil schemes and I'm working on that.
Your interrupt is simple enough. It can all be done in assembly language, and you don't need an extra stack. So there you go. You're not doing a C call in the first place.
You're a sick man.
Yes.
Why would you write an assembly interrupt? Oh God, we're trying not to write an assembly. That's why compilers exist.
Yeah, but interrupts are take a piece of data, put it someplace, and set a flag. That's it. You're done. If you're doing more than that,
it may just be set the flag.
Yeah.
Well, I'm actually in violent agreement with you. Although I found in practice setting the flag is more than a couple of instructions. Like especially things like YORT handlers and things like that, where you actually have to have concepts like, are we in a flow control state? I would posit that the number of schemes where that's a viable strategy is a subset. Where, yeah. Well, I mean, I'm saying the difference between like a few instructions versus a few hundred.
Yeah. To me, interrupts are something like read the data A, put the value over there.
Exactly. Yes.
And if you're putting a few hundred instructions in your interrupt routine, something's wrong.
I agree completely, and that's actually the reason.
That's the way I feel about it.
That's the reason for I essentially refitted the multitasker that MP ships so that it integrates the sleep.
Yeah.
Because what it means is that you have lots of tasks, and then your interrupt handler's job is simply to wake a task.
Yeah.
Yes. That's all it needs to do.
And unfortunately, in the world, that has proven to be kind of interesting in the world of Forth, because getting these interrupt handlers that are written in C, which is usually just kind of template stuff and cookie cutter things, to interact with Forth it's not that hard, but you got to pay attention. Yeah. And so what I ultimately would love to have is I would love to have some low overhead way of actually just letting Forth run something, because then I can, for instance, I have primitives like send a message, set a semaphore, wake a task, and that stuff is actually all a lot cleaner in Forth than it is in C. So, and then this is the example. You can actually write interrupt service handlers at the prompt in this environment. It's my God, that's evil, but it's really cool.
Dynamic ISR.
It's all these things are all possible. The M0 architecture makes that kind of hard.
The only problem with me in that is I make too many typos.
Right.
I have to run it several times to make it work.
So links, you can have them later. All right, so this is the point where I'm going to rant a little bit. This chip apparently is very popular and it's cheap, but frankly I think it sucks.
It does.
And I don't ever want to touch this part ever again. And so what's that?
Could be worse. Could be a pick. It could be a pick or 8051.
I used to think picks were awesome until I got smarter.
Since you saw any other processor.
Yeah, no, picks are really great if you love dinking around with that stuff.
Right.
But this is the part that I don't want to put down on paper, but professionally I do embedded systems all the time, and my job is actually to look at devices and choose ones for projects. And the ST Micro, I can't speak to the bigger parts, but there are a lot of parts on the market where vendors have taken existing 8 or 16-bit designs and simply changed out the CPU core. And so what you find with parts like this is that it's got kind of weird peripherals with interesting behaviors that are not well documented. On the other hand, if you look at things like TI's offerings, which started 10 years ago with essentially a clean slate, or the other one that it's a really nice device family is the Energy Micro and Silicon Lab stuff, which is also a clean slate design.
The one that changes is the 407.
Yeah.
Right, that 407, that one, you could remap everything.
Yes.
All the pins, everything, it just completely.
And it's probably almost too much.
It's probably, it would be too much. But if you needed to plug it into someplace else.
Yes.
Right.
This stuff has value.
Almost dropping it into the board with no changes.
Yeah. I think that's ST's pitch. Basically, you can have a pin compatible change with the right software.
But those discovery boards for that are a little more than $14. They're about $30 now.
Right. So I started looking at this. Well, so the Energy Micros boards are on the order of 30, but they have fancy features. I've shown you these. But there's a lot of low-end Cortex M4s, and like a TI Launchpad is $14, and that's for a part with like 256K of flash and 32K of memory that you can do a lot of stuff with. I think these devices are really probably better choices for beginners because they have really nice fault handling. For instance, I don't know if I've demoed this for you all, but I actually have memory protection working on the bigger chips. If I go to the fourth prompt and I stomp the wrong memory, instead of crashing my part, it'll restart fourth. So things like that are actually really good for beginners because it prevents you from shooting yourself in the feet. And then the fault diagnosis thing, frankly, I was really sad when I learned this because I have nice fault handlers that print all the registers out and say, yo, doofus, the instruction at this address faulted your processor when it tried to access this piece of memory, and it makes debugging way faster. Because the classic mistake with these devices is trying to access something you forgot to turn on. It happens all the time. And the other thing that's kind of nice is all the big devices, they run M0 code. So you can take this light compiler and just run it on bigger chips. It'll be inefficient, but that's okay. So anyway, end of rant. Last call. Suckers.
It's interesting that I'm at the early stages of a very similar kind of event here. Although eForce is quite a bit smaller.
Yeah.
It's just a little over 8K, 8.5K.
8K?
8.5K of this memory.
So
it's pretty tiny.
I've been meaning to try it for a while, but I'm not.
But so far I haven't got it working, but I'm getting close.
I'll be glad to get you set up on that part. Give me about an hour. Yeah.
Could I impose upon you to send your slides in to Dave?
Yes.
And if you could maybe send a note to the email list about your favorite ST Explorer board?
I don't have one.
The one that you held up and said,
Oh.
oh, this is the one I like the best.
I didn't say that.
Okay.
I said this is the one I was asked to port to.
Oh, okay.
Now the reason for this, from what I understand from
You held it up as an example of a board
Yeah.
that is usable and does have the JTAG
I did.
on it.
There's a lot of things on the market like this that kind of meet this basic setup. There's an integrated.
Something like better.
Oh yeah, definitely. There's lots of better. Well,
Send a recommendation for the kids in the high school robotics class.
I will.
To,
I'm already working on that part.
If you have an Arduino, you can always make it a JTAG.
Yes.
It's not impossible, but the whole thing is you got to understand how to access the registers.
Yeah. The Arduino setup is it's surprisingly nice.
Yeah, I don't know what JTAG standard they're using in there. I'm a little bit familiar with 1500, but I'm not.
None of that stuff applies to this. 1500 is a
Just instructions registers at first level, right?
So most of the small devices use something that ARM calls single wire debug, which is a 2-wire format that logically is not unlike I2C, but it's essentially an 8-bit instruction code and a 32-bit data packet. And essentially the ARM debug model is there's a set of 8 registers that do everything you need. They do things like set the processor into states. There's a memory access port. So essentially there's 8 registers that do everything you need. In a JTAG environment, you're simply setting up the JTAG chain so you're accessing these registers. But there's lots of debug probes that speak this protocol these days because it's the standard. You can also use traditional JTAG depending on your software stack.
I'm just using the serial port.
Yeah.
I
Yeah.
can load it and look at that.
Yeah. Now that I've got M0 support all figured out, I can pretty much port to a new board in about an hour. Basically the recipe is you start with the vendor's hello world example for a UART, and then you do a little plumbing and you're done. So anyway, thanks.
Yeah, I know.
I'll let you tell them.
I'll turn on the microphone at this time.
Let me make sure that it's coming through.
And this particular board here, apparently that's the way they always designed it.
Some of you may recognize me as Kevin Appert, program chair.
Hi, Kevin.
Hi, George. For my crimes, I'd just like to wish you all a Happy New Year. Thank you for your participation. We're the Silicon Valley Fourth Interest Group. Our monthly meetings are our main activity. There is a website with various pieces of code and other information about Forth, the programming language. We have a email list that you're welcome to subscribe to. If you would like to subscribe, send an email. My email address is on the monthly agenda. You can ask Google when is the next SVFIG meeting, and it should bring you right to the agenda page on a good day. If you use your email client for that, it may not work. I don't know why one would want to, but somebody did. But we digress. Anyway, that's all. Motion to adjourn is always in order. It takes precedence and it's not debated.
Oh, okay. And now I can stop.